Hello everyone, this is Lanston Davis and today we are going to discuss about Hamming code generation and checking. So let's get started right away. First we have Hamming code error detection. So what do we need Hamming code? For example, if a sender were to send a packet to the receiver, how do they do it? They send in the form of a packet but through a channel. And what if the channel happens to be noisy or happens to be crowded or happens to have data traffic? The data bits within the packet gets changed and hence resulting in a confusion between the sender and the receiver, and that's why RW Hamming proposed a method to resolve this issue for a change in single bit error and helps them to correct it. And if there are a 2-bit change, it would help them to detect the error, but they unfortunately cannot correct it. So let's get further on with the details. And yeah, and we are going to understand this more with by implementing a 7-bit Hamming code. Okay. So let's start right away, and yeah, we have this template over here, and I have assigned D7, D6, D5, P4, D3, P2, P1. So what do these basically represent? The P1, P2, P4 represent the parity bits, and the D7, D6, D5, D3 represents the data bits, and the 1 or the integer allotted to the right of every string is the index of that particular box. Okay. And yeah, and so by counting the number of these, you may see I have allotted 4. I have a 4-bit data bit, and I have 3 parity bits. And how are these allotted? Okay, how are these first allotted in this template? So first, basically what they do is that they allot the P1 indexes, and then they just simply put their data bit where the P index parity bit indexes are not there. So allotting the parity bit seems to be the issue over here, and the parity bits are allotted, they are allotted to the indexes according to the formula of 2 power n. So you may see over here we have 2 power 0, that is 1. So yeah, the n represents the set of whole numbers. Okay. So what is the first whole number? 0. To what is 2 power 0? 1. What does 1 represent? 1 represents the first index. Hence 1. Hence we are putting a parity bit over in the first index. And then what is 2 power second whole number is 1. And what is 2 power 1? 2. And when the second index, what does the 2 represent? The 2 represents the second index, and in that second index we are putting the second parity bit P2. Similarly for 4 and similarly for 8, but unfortunately we are only taking implementing a 7-bit Hamming code, hence there is no use for the 8 index. Okay, that's why I'm not showing it here over here. And now on how do I allot on, what value should I put for these parity bits? At initial itself you may get the data bit value correct. You're sending the message, it's changed into ones and zeros, and then they're put over here. But P4, P2 and P1 are generated by us, or to be more, the Hamming code algorithm. And what is that algorithm, or what is, or how are we putting or finding the values for this P1, P2 and P4? Well, in accordance with the 2 power n, there's also one more function that is to be done in according to indexes, that is finding out the proper data bit for the parity bit uh, values. Okay, what do they do is that they find out the even parities of D3, D5, D7 for the P1 bit. But you may now arouse a question, how am I allotting it as D3, D5, D7? That's why we have this table right over here, the decimal binary conversion table. So here on the, we have, do not consider the 8s, 4s, 2s, 1s in this binary, but rather just consider the indexes or the places of this ones within these table. Okay, so at first you have to take the last row 101010 into consideration, and wherever you find 1 on the last bit, okay, in this 4 bit, wherever you find 1 on the last bit, on accordance with its correct decimal value, that decimal value should prove as an index for that data bit, excluding, importantly, excluding the index mentioned in the parity bit. So we have here P1, So 0 plus 1 is 1. Let's consider the last index. So last bit, that is 1010 over here, and you find 1 over in the first place. And what is its corresponding decimal value? That is 1, and hence exclude put 1 over here, but unfortunately 1 is in the index of the parity bit. Exclude 1, then find elsewhere 1 is present. That is 1 1 1 1. That's third place, fifth place, seventh place, third place, fifth place, seventh place. Hence what you're doing is putting the data bit D3, D5, D7, finding out its even parity, and putting in the place value of P1. I think you understood this. And similarly, this is done for 2 power 1. Okay, as for 2, look in the second place, P2, look in the second place. Here you find 2 over here, then you have 1 in the for the third value, and then you find do not have any ones for the fourth, fifth values, then you have 6, 7 values, and that's why excluding the P2, we should not, as I told you earlier, we should not index the parity index. Other than including the parity index, other than include all the indexes for as by referring to this table. So we have third index, we do not have 4, 5. We have sixth index, seventh index. The third, sixth, seventh index, we have D7, D6, and D3. Hence, you find the even parity for this, and then mention it in the P2th index. Similarly, for P4, wherefore look for 4 in the, I mean the third. This is the third, correct? 0, 1, 2, 2 plus 1, 3. The third place, look for 1. Oh well, you find 1 over here. And what is its decimal value? 4, 5, 6, 7. Well, you do not have for 8. And then exclude the fourth value since it is P4. P4 it has a fourth index as allotted for parity. So other than allotting for parity, you have 5, 6, 7. Put their data bits over here. Find out the even parity. Put the parity bit, even parity bit over here in the place for P4 in this bit. Okay, so you already have, summarizing once again, you have the D7, D6, D5, D3 values as per given by the message by you, and then you find out the P4, P2, P1 values by looking into this table, finding out the ones as for their index, and then finding out the even parity of those bits, and then allotting the answer to this P1, to this P2, and this P4 respectively. I hope you understood this. Next, we have Hamming code error generation in the form of an example. Let's consider the data bit 1011. As I told you earlier, first you assign D7, D6, D5, D3. I mean, for you first allot the indexes freely for P1, P2, P4, and then put D3, D5, D6, D7, and then put the respective values accordingly 1011. Now, what you find is the parity values. How do you find the parity values? You find it using even parity. And on what method? D3, D5, D7, compare D3, compare D5, compare D7. That's 111. What is this D3, D5, D7? I explained to you in the previous slide. This D3, D5, D7 is chosen in accordance with this binary table. So, yeah. So, what is this D3? D3 is 1. What is D5? D5 is 1. What is this D7? D7 is 1. So what do? You find out the even parity. What is the even parity? 1 allotted to P1. Okay. And next, similarly, we have P2, P2, D3, D6, D7 as explained in the previous slide. What is D3? D3 is 1. What is D6? D6 is 0. What is D7? D7 is 1. What is the even parity? 0. Hence put it in P2. Similarly for P4, D5, D6, D7, 101, that is 0. Put it into P4. And this is your final sent Hamming code that's to be sent from the sender to the receiver to enhance less confusion. Okay, so you may not know its application just yet. Well, let's now do checking at the receiver's end. So till far we have done everything at the sender's end, and now let's understand this a bit more in the receiving end. In the receiving end, we have the Hamming code error detection example checking. So how do you check? So you have a received Hamming code over here, or you just say the received code which has Hamming algorithm embedded within it. So we have here 1110101, but unfortunately, thinking back, you only sent 1010101. Okay, you only sent 1010101. Well, what do you find over here? You have received it as 1110101. Sorry, 1110101. So you happen to notice a change over here, one. Okay, so at the first glance, you may not know because you are not manually checking it. The computer is checking it. But how does the computer find out? It again implements the same algorithm, P1 comparing D5, D3, D5, D7. Calculates the event parity, which happens to be 1, and you find P1 to be 1 over here. No problem. Now let's check for P2. P2 compares D3, D6, D7. It finds out the event parity. What happens to what is D3 1, what is D6 1, what is D7 1, what is its event parity 1, but unfortunately P2 happens to be 0. You find an anomaly over here, and then what you see? P4. P4 we have D5, D6, D7, 1, 1, 1. What happens to be 1? What unfortunately P4 happens to be also 0, and you find an anomaly over here. Hence, now you can conclude that there is a change in bit, there's a change bit over here in this 7-bit Hamming code. Okay, and that D6. Okay, at first glance you find it over here. D6 is a problematic error by comparing the previous sent code and the received code. But as for a computer in real life situations, you only receive the received code. There's no sent code over here. Think it as basic common sense. But then, how do you find out the D6 uh, uh, index is the error bit? You find it out by calculating by or doing Hamming code checking. Well, I'm not doing Hamming code checking over here. Sorry, not checking, correction. Well, other than that, everything happens to be perfect. Everything seems fine. And I guess you understood generation and checking properly. And that's it, guys. That's it for today. And yeah, you see it over here. 0 not equal to 1, 0 not equal to 1 as for P2 and P4 comparison. Well, I would like to conclude my presentation animation video over here. And yeah, and you may conclude that this is a wrong message and proceeds for error correction. And that's how you understand that whether the sent code is same as the received code. And the correction is done further in the further processes. But unfortunately, I'm not doing it. And hence, thank you for watching, guys. Any doubts, please comment. Thank you so much.